And we're back. Welcome back from the weekend and happy Tuesday. Today, we'll pivot with a deep dive into details of the transport layer. But before we begin, some administrative bits. Project number 3, the HTTP Wireshark, is due Tuesday, this Tuesday, today, 16th of February, at 11:59 and 59 seconds p.m. That's 1 second before midnight. Okay, so our goal in our study of the transport layer, we'll understand principles behind the services afforded by the transport layer to the application layer. And that includes multiplexing and demultiplexing, that singular channel of data coming from below from the network layer, as well as above from the application layer. We'll also look at reliable data transfer services and what reliability means. And we'll look at flow control and congestion control is efforts underfoot by the transport layer to limit the rate of sender sending of data in response to different other factors in the system. We'll also look at the transport layer protocols, two major flavors, UDP and TCP, the connectionless transport, unreliable datagram protocol, and the connection-oriented reliable transport, namely transmission control protocol. And we'll also look at how TCP congestion control specifically works instead of generally. So let's take a look at the services. Now, the whole purpose of the transport layer is to provide the illusion to the applications above that they have a direct end-to-end connection to the transport layer on the other side, the other endpoint of this communication. And so that requires a lot of doing. Now, certainly the transport layer interacts with the network layer, which does not have the same guarantees, and we will certainly look at details of the protocols and considerations in play in order for the transport layer to be able to offer these services. And so the transport layer, through the socket APIs, presents a logical end-to-end transport, the carrying of these units, these chunks of data, the packets, from one endpoint's transport layer to the other endpoint transport layer. Now, the application has no idea what's happening below. Application layer just sends its messages into the socket. And some of the things the transport layer does, for one, on the sender side transport layer, it breaks application messages into chunks of data called segments. And so when we talk about packets from the standpoint and perspective of the transport layer, we call it a segment because it includes other pieces of information that are meaningful to the transport layer on the other endpoint in this communication. And so the transport layer breaks the application messages into segments, and it passes those segments with a little bit of other information, transport layer header information. It passes that segment to the network layer below. And then it makes its way across the internet and ultimately is delivered to the transport layer on the other endpoint by the network layer below. And the receiver side transport layer takes these segments and reassembles them to reconstitute, if you will, the original message that was put in the sender transport layer endpoint. And so the receiver side reassembles these messages and passes them up above to the application layer above it on the receiver endpoint. And so you can have more than one transport layer protocol available to applications. And for the internet, there are two major flavors of transport layer protocol, namely TCP and UDP. In the book, they have a human example to describe what the relationship is between the network layer and the transport layer. The network layer describes the logical communication between hosts, and more correctly, between network cards. And so the network layer has information that is meaningful to all of the network layers scattered around the network, and that is namely the IP address. And the transport layer provides then on top of that logical communication between the processes. Now, of course, every host has more than one process, i.e. more than one program in execution running on it. And so now that you have this datagram from the network layer delivered up into the transport layer, part of the transport layer's responsibility is to then identify and push that particular segment data, i.e. the message when it reassembles, to the correct process. And so the transport layer relies on the services of the network layer, and it adds capability to the network layer, this ability to identify individual processes in the application layer above. And so the analogy used in the book is that you can imagine there are two houses. You have Anne's house and Bill's house. And each one of these houses you can think of as a host. And let's say Anne and Bill both have 12 children each. They're buying a lot of milk. So when you send a letter to an individual in the other house, well, you can think of a letter almost like an application message, and that letter is in an envelope. Now, of course, the transport layer then multiplexes on the sender side. Let's say one of Bill's children wants to send a letter to one of Anne's children. What do you put on the letter? You put the host address, the network layer, the house. So once it gets to the house, Anne gets this mail, and then she looks at the child's name, and that's like the port number, in order to identify to which child this particular packet or letter, that message, should be sent. And so the network layer protocol acts like the postal service. They figure out how to get this letter to the correct host, and that host has installed on it a network card in real computation. And so this is a very well done example. Please make sure you're looking at this example in the text. And so transport layer protocols offer two major flavors of services. One is the reliable in-order delivery. That means that when you send a first byte, a second byte, a third byte, the transport layer, in TCP's case, guarantees that those bytes will be received and assembled in the same order in which they were sent. So the first byte gets delivered as the first byte, second as the second byte, third byte as the third. The TCP, or reliable transport, also offers congestion control, flow control, and connection setup, where congestion control refers to the slowing down of the sender in response to the perceived ability of the network path to support that bandwidth. And so the thing that it's reacting to for congestion control is router congestion. Now, flow control is also the slowing down of the sender in response to the amount of free buffer space that the receiver has. And it kind of makes sense. Why send more data than can be stored on the receiver? Because if you do, you're going to end up dropping that data and just wasted all of that work it took to transmit the data and propagate the data across the many links between the source and the destination endpoint. And then it also lastly has connection setup. Now, connection setup is the establishment of the resources prior to the exchange of messages between the sender and receiver. And so in that first round trip we talked about a few modules ago, that the client that initiates the connection asks the server, do you have the resources in order to engage in this reliable transport? And it answers back yes or no. And so that connection setup is the establishment of those resources, and that's done through one round trip. So a message goes from the client to the server requesting a connection. Server checks its resources, allocates them, and returns back the response yes or no. And after that, that means the server is able to hold up its end of the bargain for the server side responsibilities for this reliable transport. The unreliable service, UDP, Unreliable Datagram Protocol, has no guarantees. And so your data can be delivered in a different order from which you sent. And it's a no-frills extension, very minimal extension, that only identifies processes on the receiver endpoint, or it identifies the sender on the sender endpoint in this UDP communication. And so the reason why UDP is there is because all of this reliability comes at a cost. If you have reliability, that is computation that takes away from sending, and you have a slowdown. And so UDP has just out-and-out raw speed. And so the services that are not available are delay guarantees, so you can't upper bound how long it's going to take to have a packet delivered between the source and the receiver endpoint, as well as bandwidth guarantees. What is the rate at which things will go? Can you guarantee a certain minimum bandwidth? And as we saw in the previous set of modules, that the bottleneck link is the one that constrains the end-to-end throughput as perceived between the sender and receiver endpoints in the application layer. And so let's take a look at this multiplexing and demultiplexing. And so here we have three different applications. We have application and host on the right-hand side and on the left-hand side, and they're running processes P3 and P4 respectively. We also have a server in the center of our diagram. So this is our server, and this is our client. Let's call that client 1 and client 2. So client 1 and 2 are running P3 and P4 respectively, and the server is running two processes, process P1 and P2. And if we look at this, there's an outbound edge from P3 sending data from that application layer through its transport to our server process P1, and then application P4 running on the second client is sending data to process P2 running on the server. Likewise, the server, it receives data and sends back responses, and so P1 process on the server in the center is sending a response back to P3 on client 1, going off to the left, and likewise process P2 on the server running an application layer through its socket interface is sending a response back to client C2, its process P4. And so here, these golden rectangles, those are the sockets, and you'll notice they straddle the seam between the transport layer and the application layer, and that's just to connote that it's a service that both receives packet information in the form of messages from the application layer above, but also delivers segment that message data from segments within the transport layer going in the upward direction. Okay, so we can handle data from multiple sources, and here we see that the application layer for the server in the center is getting inbound data from two different clients, C1 and C2. And likewise, these two processes running on the server, that server's transport layer is handling outbound data to two different clients, C1 and C2, running on different machines across the internet. And so in order to do this, you need to multiplex the connection to the outside world afforded by the network layer. And so at the sender, it handles data from multiple sockets, and therefore, in order to do the sharing of that single channel of data, so to speak, from the network layer for that particular host in the center, the server, you have to add other pieces of information, and those pieces of information are called port numbers. And so the port number on the transport layer is responsible for identifying which process, and more correctly, which socket is the intended destination of an incoming packet, or which socket was the source for a particular outgoing packet. And so the header information is used for this delivery. And so when we refer to packets from the perspective of the transport layer, we call them segments. So we say a transport layer segment because that includes information that's meaningful to the transport layer. And so this is the schema for a TCP UCP segment format. And here we have 16-bit numbers for the source port number and the destination port number, and we have some other fields. And then down below, we have the payload data, and this is the message data either from some application, from the application layer above, or destined to go or be delivered to the application, the destination port number, associated with the application layer above. And so each datagram has two pieces of information. It has the source IP address, and remember the datagrams for the network layer below. And so the network layer gets the datagram and delivers it into the transport layer. And so each datagram has a source IP address to identify the source machine or host, and a destination IP address to identify the destination host or network card. And each datagram also carries one transport layer segment. That segment is inside of the datagram coming into the network layer. And so the network layer strips off the network layer header information, revealing the segment, which it then sends to the transport layer above. And so each segment then has pieces of information that are meaningful to the transport layer, and these are the source port number associated with the source process on that source machine at that source IP address, and the destination port number associated with the destination process or application on that host identified by the destination IP address. And so the host uses both the IP addresses and the port numbers as information to direct the segment to the appropriate socket, which then ultimately gets to the appropriate application bound to that socket. And so in the connectionless version, recall that when we created a UDP client and server, we created a datagram socket. And when we created that datagram socket, we gave it a port number. Now, of course, when you send, because it's connectionless, you need the destination IP address and the destination port number. And your network layer on the sender side already knows what the destination IP address is. And so you create your socket and you give it some coding or encoding or representation of the port number that you are trying to reach. And so when the host or server receives a UDP segment, it checks the destination port number in the transport layer and then directs it to the socket, and then ultimately from the socket it gets to that application that owns that socket. And so IP datagrams with the same can have the same destination port number, but they can have different source IP address numbers and or different source port numbers. And so you can have multiple applications on the same machine send, or multiple applications on different machines send to the same destination IP address and port number. Okay, and so this is an example of connectionless version of demultiplexing from the perspective of the transport layer. And so we start out, we create a socket, and that socket is associated with port number 9157. And we also, on the client machine on the right, process P4 creates a datagram socket with port number 5775. In the center, we have a server that creates a datagram socket with port number 6428. So then we have process P3 sends a message for process P1. So source port number in the transport layer in the UDP segment is going to have a source port of 9157 and a destination port number of 6428. Then, when process P1 sends back a response, the source port number, it's reversed. Its source port is 6428, destination port is 9157. And switching that destination port is how the transport layer on the left-hand client machine is able to direct that segment to process P3. So likewise, at the same time, process P1 can send to process P4 and can receive back responses from process P4. Now, one of the questions is, what is the source port and destination port in this case? So I'll give you a minute to think about this. Please pause. Okay, so now that you've unpaused, when we look at the source port number, of course, the source port number is going to be port number 6428, because that's the source port number of process P1 socket. Destination port number is going to be 5775, and then we just reverse them for the outbound packet, the response from process P4 back to P1. So the source port is going to be 5775, and the destination port is going to be port 6428. Okay, very good. So let's look at the connection-oriented service. How do you demultiplex and multiplex the connection when you have reliable data transport, namely transmission control protocol? And so the socket is identified by a tuple, a set, or 4 different pieces of information. It's the source IP address, the source port number, destination IP address, and destination port number. And then when you demultiplex, the receiver uses all 4 of these values in order to direct the segment to the appropriate socket. And so a server host then can support multiple simultaneous TCP sockets, and each socket is uniquely identified by its own 4 tuple involving the source and destination IP address and the source and destination port number. And so web servers, as we said a few modules ago, can have different sockets, one connection socket for each client on the other side of the internet. And if we use non-persistent HTTP, you're going to have a different socket for each fetch request for each one of these objects inside of the web page. And so this diagram is in the book, and it talks about the 4 tuples used to represent unique connections, logical end-to-end connections between processes facilitated by the socket through the transport layer. And so here, between process P3 and P4, on the inbound side of process P3, source IP and port number are address B, and let's assume that we have IP address A, for the machine on the left, IP address B for the server in the middle, IP address C for the host on the right, the client machine on the right. And so for inbound to process P3, we have source IP port is source IP and port number are IP address B and port number 80. And then on the outbound side for process P3 on host A, the source IP and port number is going to be A, that's the host, port number 9157. And then the destination IP and port are IP address B and port number 80. Now you notice here on the inbound direction versus the outbound direction how the source and destination IP address and port numbers are reversed. Likewise, when we look at process P5, same deal. Source on the inbound side for host C, process P3. On the inbound side, we would have source IP address is going to be B, and the source port number is going to be, let's see, port 80. And then if we look at the inbound, the outbound side rather, coming from process P3, that was the inbound side. Took me a moment. On the inbound side, that would be a message from process P3 going to process P5 on the server in the center. And that's going to be source IP address and port number are going to be IP address C, because that's machine C on the right, and the source port number is 9157. And then, of course, this is a web server, so the destination IP address is going to be IP address B, and the port number is a well-known port number for HTTP servers, that's port number 80. Okay, and so each one of these tuples uniquely identifies the connection, and you can have this specificity even if you have multiple connections going to the same process from different machines. If it's from different machines, they can have different IP addresses. If it's on the same machine, they'll have the same IP address but different port numbers. Okay, so let's take a look at connectionless user datagram protocol. This is RFC 768, and it's no frills, bare bones Internet Transport Protocol. It provides best effort just on top of the network layer. It only adds minimally a little bit of IR checking and the multiplexing using port numbers. And so segments can be lost and they can be delivered out of order to the application. It's connectionless, so there's no handshaking around, and each UDP segment is handled independently of others, so you have to address them uniquely. There's no connection information. And so how is UDP usually used? In applications that can tolerate loss, such as streaming multimedia, things like streaming sound. Domain name service uses UDP. Why does it use UDP? Well, because it's fast and all of the UDP queries and responses fit in a single packet. SNMP, Simple Network Management Protocol. Well, it's used if your network has issues to manage your network, and so it uses UDP because you want that information to traffic around your network as fast as possible. You can implement a semblance of reliable transfer over UDP, but if you're going to add that reliability, you do that at the application layer endpoints, namely in the form of buffering and other types of recovery mechanisms. And so this is the UDP segment header. It's very simple. We have the application payload data down below, and then we have the source port number and destination port number. We have the length field, which counts the number of bytes for the whole UDP segment, including the header information. And then we have this checksum, which offers error checking. And so there's no connection. It's very simple. Has a small header size, and there's no congestion control. So UDP can just send data as fast as it wants to without regard to whether or not the receiver has buffer space or without regard to the congestion status of the routers along the pathway between the source and receiver endpoints. And so what does this checksum do? Well, this checksum is a detection mechanism for bits to get flipped, i.e. corruption. And it's transmitted in segment and then recalculated at the endpoint when the segment is received, and it compares what was sent to what was calculated. And so what do the sender and receiver do? Well, you treat the segment contents, including header fields, as a sequence of 16-bit integers. So every block of 16 bits, it treats it as an integer, and then it computes the checksum. It's an addition, the ones, and then it does the one complement of that resulting sum. So it flips all 0 bits to 1s and 1 bits to 0, and it takes that resulting value, the checksum, and it inserts it. So then the receiver, when it gets this UDP segment, it computes the checksum from the bits of the segment, and then it compares that to what was stored as payload, and then it checks to see if they're equal. If they're not equal, that means an error was detected. If they are equal, there's no error. But it could be something that an error was there, but it got through. It doesn't detect individual bit errors. So here's an example of computation of a checksum. And when you look at this computation of a checksum, you have to remember base 2 arithmetic. Now, base 2 arithmetic says if I have a 0 and I add it to a 0, that result is a 0. If I have a 0 and I add it to a 1, that result is a 1. If I have a 1 and a 1 and I add them together, that's a 0 with a carry out of 1. If I have a 1 and a 1 and I carry in a 1, well, that's a 1 and a 1 and I carry out a 1, and that's a 1 because I add that 1 that I carried in. It's a 1 with a carry out of 1. And so we use these 3 or 4 scenarios to add the individual bits, and then we compute the checksum by taking the 1's complement. And if we get a carry out on the left-hand side out the most significant bit, we just add that back in to the least significant bit. So here we go. We have these two 16-bit integers. So we have 0 plus 1, that's a 1. 1 plus 0, that's a 1. 1 plus 1 is a 0, carry the 1. 1 plus 0 plus 0, that's 0 plus 1, that's 1. It's a 1. 0 plus 1, so 1. 1 plus 0 is 1. 1 plus 1, 0, carry the 1. 1 plus 0 is 0, that's 1. 0 plus 1 is 1. 1 plus 0 is 0. 1 plus 0 is 1. Correction. 1 plus 1 is 0. Carry the 1. 1 plus 0 plus 0, that's 1. Write down a 1. 0 plus 1 is 1. 1 plus 0, that's 1. 1 plus 1 is 0. Carry the 1. So we have a carry in of 1. 1 plus 1 is 0. Carry out a 1, but we add 1 to that 0, and it's a 1. So we carry out a 1. So now we take this 1, and we add that back in here. So we add that 1 here, because it carried out. We just wrap it back around. So if I take a 1 and add it to 1, that's a 0. Carry the 1. And we have 1 plus 1 is 0. Carry the 1. And that's 1 plus that 0 that's there. It's 1. And then everything else we write down. 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, and 1. So now this is our sum. And to now compute the checksum, we take the 1's complement of each one of these digits, going from least significant bit to the most significant bit. So here we have a 0. We flip that to 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, and 0. And this becomes the checksum for that sequence of two 16-bit strings of 1s and 0s. Okay, and that would be our calculated checksum. We will put that in the checksum field, and then when we get that packet, we recompute the whole checksum, 16-bit integers at a time, and then we compare what we calculated with what was stored. All right, so that is checksum, and it's the error checking mechanism used in a UDP packet. It doesn't check or detect errors on a 1-bit granularity, but for block or bulk flips or changes of bits, which is usually the case, this will detect it. All right, so that's all I had for today, and with that, we'll end there. And as usual, please stay healthy, stay safe, and I'll see you all on Thursday.